This is a recap on how cryptocurrencies work with an example in Bitcoin. So this is an imaginary state of the Bitcoin network. We have here a bunch of nodes connected. Some are better connected than others, but this is just natural in a distributed system. And then we have some current blockchain structure going on here. In this case, we just have two blocks. The first one is also called the Genesis block. And then within each block, we have the header. And then on the bottom, we have listed all the transactions. And in the header, we have the block's hash, the previous block hash. In this case, because this is the first one, there is nothing. We have the nonce and the Merkle root. And the Merkle root, if you remember the video about Merkle trees, it's just that binary tree where you hash together the transactions. So in this case, we have transaction 1 and 2 hash together, create another hash, 3 and 4 hash together, and then you propagate this up to the tree root, and here you would have these two hash together, and that would actually form the Merkle root. This is used to validate transactions efficiently, which I will mention in a second again. And now Alice wants to make a payment to Bob's ice cream stand to buy some really expensive ice cream using that network. So let's say Alice is here and Bob is here. So Alice is going to create a transaction. She's going to say, I, Alice, am going to pay Bob, let's say 1 Bitcoin. I said the ice cream is expensive, right? So Alice will sign that with her private key, and then she will broadcast that transaction out into the network. So you can see she is just connected to one node in the network first, but then that node picks up the information, keeps on sending it out to the ones it is connected, and so the message will propagate all the way to Bob. But at this point, Bob has no confirmation about this payment yet. In fact, that information here just ends up on a pile of other information about transactions which haven't been validated yet. Now the miners come in. The miners grab a chunk of that pile of information, or depending on how big the pile is, maybe the whole pile, and they will start to solve the hash puzzle. So they will take as an input the current blockchain header hash, so the block hash of the newest block in the blockchain, plus they will add all the information about transactions they grabbed here. Let's say this is transaction 10 here where Alice pays Bob. So it will be a whole bunch of them, transactions, all concatenated together. And they try to find that nonce, that single piece of string they can add here to generate a specific target output. And let's say in this case we want to generate a hash function output with 5 zeros in the beginning, and the rest can vary. So then let's say John found a solution, and then John gets to append a new block, and it will have the same kind of ingredients here in the block header. So he will publish that hash here he generated with the 5 zeros. Then he will link here back to the previous block with a hash previous. Then it will also include here the nonce, so his solution, so that other nodes can check that he actually did the work. And again, the Merkle root, again generated here with the same structure. He will take all the transactions he grabbed including transaction 10, Alice and Bob, build that binary tree, Merkle tree, and include the root in the header. So as soon as John finds this new block and generates this structure, he sends the new block out into the network as fast as possible so that the other nodes can start mining on top of it. Only, of course, if the block he sent only contains valid transactions. But how do the other nodes confirm if the transactions are all valid? Let's look into that a little bit in more detail. So here is a pretty straightforward approach how we could do this, right? How we can check if some person sending some currency in the network has enough funds. Well, we could do some account-based system, right? So let's say we have a chain of transaction that starts with 25 bitcoins going to Alice for creating a block. So that was initial 25 coins minted from the mining process. Then Alice pays 15 to Bob. Then Bob pays Louis 10. And then Alice pays again David 5. And also Alice pays 5 to Alex. Now to evaluate if any of these people have enough money to actually do another transaction, for example, the next one could be Alice pays 5 to Carol, we would have to store the current balance for each person. So we need to have a account store and update that every time something happens in the system with the transaction. So we would have an account for Alice, for Bob, for Louis, David, and Alex. And so we have to update this data structure every time we have new transactions happening in the system. So we would have here initially 25 bitcoins coming in for Alice for mining a block. Then we have 15 going out and 15 coming in for Bob. Then we have 10 going out by Bob's account and 10 coming in on Louis's side. Then we have another 5 leaving Alice's account, entering David's account. Another 5 leaving Alice's account, entering Alex's account. And at this point we would have total balance in the system of David, Alex owning both 5, Louis would have 10, Bob would have 5, and Alice would have 0. And of course the sum of that is 25 bitcoins because that's what we initially created here in this mini world. And so the next transaction here, Alice pays Carol also 5, would be invalid, right? But that's not a very efficient approach to this. So instead of focusing on accounts and their balances, we're going to focus on transactions themselves. We're going to have inputs to a transaction and outputs. And if anyone has a claim to a unspent output of a transaction, he actually owns those coins, right? So this is our same set of transactions, just transaction based. So we have 4 transactions. We have the first one, input nothing, generate 25 bitcoins out of thin air to Alice. Then as an input in the next one, we have the first transaction, and then as an output we have 2 actually, because we have always to spend the full amount of the input. So Alice pays Bob 15 and then she has to return to herself 10 so that she actually spends the full 25 bitcoins. And at this point we have 2 unspent transaction outputs, By the way, these are also called UTXOs, unspent transaction outputs. Then we have next the input 2-1, so this one right here, the first transaction output from the second transaction. So, and we're going to spend that like so. Bob pays Louis 10 and Bob returns 5 to himself to spend the full amount of 15. And then lastly, we're also going to use the second output from the second transaction. So 2-2, Alice pays Alice 10, and we're going to use those 10 to pay David 5 and Alex 5 as well. And at this point we can see, okay, we spent everything from the output of 1, we spent everything from the output of 2-1 and 2-2, and thus we can simply check the set of all unspent transaction outputs, which is here, Bob pays Louis 10, Bob pays Bob 5, Alice pays David 5, and Alice pays Alex 5, and we can see that these people are able to spend those coins further and just use those transaction outputs as new inputs and, you know, create new transactions. That's how it's actually done in Bitcoin. And this is much more efficient than an account-based system where you have to look through the whole history of a person to determine if he has enough funds. Here you can just look at the current set of unspent transaction outputs, and if the value is higher than the transaction they want to actually do, then it's a valid transaction. So let's assume that all the transactions in the block that Sean found actually were using inputs that were in the set of unspent transaction outputs. So they are valid transactions. And thus, we can delete here this set of transactions that we grabbed from the memo pool of unvalidated transactions, and some other, and miners start grabbing a new chunk of unvalidated transactions and they repeat the process. So here the set of unspent transaction outputs and the memo pool of unvalidated transactions is always changing. Let's conclude this video with the characteristics based on these mechanics I just described. So it is decentralized and distributed. It's decentralized in the sense of governance. No one has control over this system, and it's distributed locally. So we have many different nodes all over the world who run the system. Then the system is immutable, so we can't just go back in time and change something in these blocks. If we do that, the whole hash structure changes and everyone can right away see that someone tampered with the data and it becomes invalid. And we have anonymous, so anyone can just participate in the system with a public key. So we don't have to actually sign up with a personal username or something. Then it's historical, so it always goes back to the initial block. We can always see the whole history. It's inclusive because we don't have to have a passport or something to sign up. Everyone can participate as long as they have internet connection. And it's public, so anyone can look into the blockchain and see what happened and when.